Any questions?
Yeah.
Yes.
If I just left it at the y equals x minus 7 squared over 2 plus 2, that'd be okay?
As long as it's a y equal, yeah. I mean, this is probably easier to see that it's a parabola with the vertex form, like the one we did.
You get, why did you square it?
No, I didn't. I multiplied it by 2. No, I multiplied it by 2.
Oh, okay.
That's not a square. I multiplied this by 2, this by 2,
Oh.
to get rid of the denominator.
Right.
Sorry,
But
it looks like a
that.
square. If as long as you give it to me y equals, if you added the 2 to that side and left it like that, you really should leave it. Whenever you do that, and you come out like this, you really should leave this in one term. If you left it in 2, it's not wrong, but do you really recognize this as a parabola? Like, you don't recognize it as a parabola, right? I mean, we do see the x squared, we know it's a parabola. But it's easier if you do it this way. I wouldn't mark it wrong. But it's easier if you put it in the parabola format. You can find the vertex. You can see that it matches your parametric equation. The whole concept of this is to take a parametric, eliminate the time, the t part, and see that it makes a rectangular one. So you want to make it so that you can identify that. And yeah, you can put it in your y equal and it will look the same exact. That's another way to check it. Again, solve for t, put it in. Again, you have another parabola, open sideways. You can see that your a is positive, and you have a y squared. There's a circle.
Wait, can we go back up to number 2?
Yeah, absolutely. Absolutely.
Yeah, I have no idea what I did, but I don't have that number.
So, did you get this far and solve for t?
Yes.
Okay, so then you replace the t in here.
Yeah.
Okay. So then I multiplied, I squared everything. This is my square this time. I squared it to get rid of this, but don't forget, did you square 6?
I just distributed the 6. I didn't square anything.
You distributed the 6?
I see where you're coming from. I did it wrong.
Okay, but you got to square this first to get the radical out of there.
Yeah, I distributed the 6.
Yeah, you got to square that first, get the radical out of there, and watch the 6. If you square it, this has to be squared.
Okay.
And so then you get a parabola. Yes, I can. Yep. When you have a radical, isolate your radical, get it by itself, and then square it. In this case, I don't think you wanted to divide by 6, but you could. You could have divided by 6 first and then squared it, and then multiplied the 36 back to the other side. Whatever works for you. Okay, the next one was a circle. Were you guys good with the circle? Good. So these are not so bad, right? And they let you recognize the shapes of these guys once you put it back into a rectangular equation. But know how to put this in your parameter one. Know how to graph this. How to set you. Everybody good with setting the windows, especially when you go to this one. Good. Okay. This one you had to use your 1 plus tangent squared equals secant squared. Use your regular cosine squared plus sine squared. If you have a tangent will give you this part. Start like this. This is going to give you a tangent squared. So then therefore just divide everybody by the cosine squared. So this gives you 1 plus your tangent squared equals your secant squared. Okay. There's a nice little hyperbola. The circles and the ellipses are probably a little bit easier. There's a circle. If you left it to me looking like an ellipse formula, I'm fine with that too. A circle is a special kind of ellipse. So if you left that, I'm fine with that. Okay, this guy, we okay with this? I always found that the students do better with the cosine and the sine because it kind of directs you to what you're supposed to do with this thing. It's a little less manipulation. An ellipse. This is an ellipse. Why? How do I know this is not a circle?
The denominator is different.
Good. It's a plus, and the denominators are different. Good. So what makes it a hyperbola? A subtract. Good. Any questions on this? No? Okay, basic pattern with these guys. Here's your basic formulas for parametrics. Put your mode in degrees because you're going to be given a degree for your angle. Don't forget the t. This t is necessary, so is this t. This is the part that brings your ball, your rocket back down to Earth. Otherwise, it would keep on going forever. That's your gravity pull. And put your velocities in, your time, your angles, turn it down. If it has any other wind speeds or anything that's going to affect the horizontal, it goes in the x. If you're standing 5 feet above ground or on a platform or whatever, then that affects the y. Okay, so now what you want to model is a ball being hit, going up, coming back down. They want to know when and where will it hit the ground, because this is your time. This is your horizontal distance. This is your vertical distance. Okay. Then they want to know, will it clear a fence, a 9-foot fence, so it's 9 feet high, when my horizontal distance, my x, is 275 feet. So you want to find out when x is 275, is y greater than 9? And if you're in the ballpark with that, you don't have to be exact on that one. If you're looking somewhere where the 275 is, if I look in between here and I know 275 is there, and I see my y's are both well above 9 feet, then that's all I need to write. I don't need to be any more exact than that. If it's close, and there will be some that are close in these, then you got to get a little bit more exact. But you'll clear your fence. Questions? Because I can pull up the calculator if you have any questions. A lot of times, this is just trial and error. The bad part is, I get it, you have to get 3 decimals. So remember how we said to do this. Set your t-step at 0.5. You could even go to 0.3, it's not that slow. 0.3 probably gets you a little bit more exact. When you're close, when you see where the y is close to the 0, go to your table. Start your table at that t-step and increment it by 0.001. And then you can get the exact. And remember to scroll over the x and the y value because they're rounded by your calculator. We're good? Stop me if you don't, because I'll gladly do this on a calculator for you. These you either get or you don't get. So you got to tell me. Again, start basic. A couple of these were just basic to begin with. You had to find your maximum height and your total distance. So sketch. The batter hits a ball, and we're assuming that he hits the ball from ground 0. He hits the ball. We need to know the maximum height here and the total distance here. Total horizontal distance. And if you think about it, when you hit a ball, a golf ball, a hard ball, a softball, that's the one you're looking for, is your horizontal distance.
Do you have to put the t for each, or can you just write it
Yeah, I need to see. I need to see your time. Yeah. Don't forget, I need to see your time because that's what's driving this. When you trace, you're tracing across your time. I need to see the T part. So you're turning, what's the maximum time? Get close to this turning point. If you're on this side or this side, go to your table and look for the turning point. Sometimes you got to scroll over to that Y because it rounds it to all the same number. Yes.
Is there a way to find like the maximum on it, like you would be able to?
No. There's no max, no min, no intercept.
Yeah,
As soon as you do trace, you can only put a value in.
Alright.
Yeah, that's the bad part. You really have to kind of do it with the trace button. It's odd because in our regular graphs, we never use trace. But in these, we do. And these, we don't get those other options. Okay, we're going to skip over. We did 5. We're going to skip 4. We're going to go to 6. I like 6, 7, and 8 because it starts real basic, and then it throws a wind speed in there. So then you can see the difference what's happening in the wind speed. So a Major League Baseball player hits a ball with an initial velocity of 103 feet per second, and watch your dimensions. They're in feet on a path 300 feet, probably to the home run fence. The fence is 10 feet high. So when you draw your sketch, he's going to hit a ball. Here's your fence, 10 feet high. He's got to clear the fence in order to get the home run. This is 300 feet, and he's got to clear that fence. And that kind of makes sense. Isn't that what a ball player does? Has to hit the ball over the fence to get a home run. So your complete graph is coming like this. Gravity is the only thing, and unfortunately he's starting at the ground again. We didn't raise him off the ground, just so that we don't throw another thing in at you. Normally he's standing probably 6 feet, 3 or 4 feet off the ground, his back. But we just left it kind of simple for you. So everybody can find this, where it hits the ground, keep track of your time again. Excuse me, if it clears the fence, and yes, he hits a home run. If he clears the fence, he hits a home run. When he's 300 feet away, his ball is almost 25 feet above the ground, and the fence is 10 feet, so yeah, he clears the fence. He hits a home run. If this was less than 10, it would smack right into the fence. And it would be a single or a double. Single if you're a very slow runner. Or if the guy was smart enough to be right at the fence at you. Alright, now we threw a wind speed in. So I kind of helped you out the other day with the wind speed. If the wind speed is in your direction, it's going to move your ball a little bit further. So we add it. But don't forget, speed is miles per hour, feet per second, miles per minute. It's got a time frame to it. So you have to still make sure that this is the same as your measurement that was in the last one. So he hits the ball at a velocity of 103 feet per second. So both of these match. So therefore, all you have to do is add the 22t. If this was in per minute, we would have to convert it. Okay, and we changed his angle a little bit, just slightly. And does he clear the fence? Yep, he clears the fence. You're close enough on this. See why I went with my X's? You don't have to get any more exact than this because I'm just about 300, and here I'm well over 300, and I still cleared that fence. So,
some above, some below.
well, yeah, if you're not that, if it's not that close, yeah, I don't really care. But if it's close, and there'll be some that might be a little bit close, but on the next group that we do, the next batch of applications, they'll be a little bit closer. But if you show me this, he obviously cleared this, even this, he obviously cleared the fence. I mean, his ball is on the down slope now, right? It's coming down after it reaches its height. So from here to here, it's only going to go down. And if he's well past the 300 feet mark, he obviously hit a home run. And then we had wind blowing in the opposite direction. So see the difference between these two? This one, that wind holds his ball up. He hits the ball, and the wind is coming at him. 22 feet per second is a strong wind. It's holding his ball up. So now, no, he doesn't clear the fence. Where is he? He doesn't reach the fence. His ball hits the ground well before the 300 mark. He doesn't hit a home run. He doesn't even reach the fence. This was a good one to see the effect of the wind speed. With keeping it a little bit simpler. Are you guys okay with this?
That was it.
That was it. I like this. Oh, we were gonna do